Hi, I'm Eric from UC Santa Cruz. I'm very glad to talk about our work on environment-agnostic multitask learning for natural language grounded navigation. Visual navigation is an important area in computer vision, and natural language grounded navigation is an essential step to enable communication between humans and machines. It is to command embodied agents to navigate in the 3D world with natural language, such as instructions, questions, and dialogue. For example, we can talk to an indoor robot and ask it to grab the plant for us. Then it may follow the instructions in the dialogue and navigate to the target location. There are typical tasks for natural language grounded navigation. The first is vision and language navigation. Given fine-grained instruction and a starting location, agent must reach the target location by following the natural language instruction. The original VLN task is proposed based on the room-to-room dataset. To go beyond the instruction following and enable bidirectional communication, dialogue is further introduced. In the task of cooperative vision and dialogue navigation, there are a navigator and an oracle. Both are given a hint. For example, the Go room contains a mat. The navigator goes towards the Go room and can stop anytime to answer a question. The oracle foresees the next best steps and answers the questions. One of the core subtasks for vision and dialogue navigation is navigation from dialogue history, where given the dialogue history, it is to predict the navigation actions that bring the agent closer to the goal room. The big issue of natural language grounded navigation tasks is the poor generalization issue. The navigation models are usually trained on a set of retraining environments and tested on seen environments and unseen environments. Seen environments are the houses that are seen during training, and unseen environments are the houses that are totally unfamiliar to the agent. It is commonly known that models tend to overfit seen environments and perform poorly on unseen environments. Moreover, data scarcity is really a big problem. Real-world experiments are usually not scalable, and data collection is prohibitively expensive and time-consuming, even in simulation. Therefore, model breaks under distribution shift, which also results in poor generalization issue. Therefore, towards generalizable navigation agents, we propose an environment-agnostic multitask learning framework, which solve the generalization issue from two novel perspectives: multitask learning to transfer knowledge across tasks, and environment-agnostic learning to learn invariant representations that can be better generalized on unseen environments. We build upon a strong baseline model for VLN, reinforced cross-model matching method, the RCM model. We introduce multitask RCM to seamlessly transfer across tasks by sharing all the learnable parameters for both VLN and NDH tasks. To avoid overfitting to individual tasks, we adopt an interleaved multitask data sampling strategy to train the model. Particularly, each data sample within a mini-batch can be from either tasks. Following prior art, we adopt a mixed training strategy of reinforcement learning and supervised learning. But note that though VLN and NDH data are interleaved within the same batch, their reward functions are different due to different objectives. We implement a discounted cumulative reward function, where immediate reward for VLN is the reduced distance to the goal location, while for NDH, the immediate reward function is replaced with the reduced distance to the goal room that contains the target object. We evaluated the effect of multitask reinforcement learning on seen and unseen validation sets. For the NDH task, we incrementally increased the dialogue input and test the effect. Progress is the major evaluation metric on NDH, and the success rate is considered the major evaluation metric on VLN. We can observe that, NDH benefits from VLN consistently. VLN benefits from NDH with more fine-grained information about the visual paths. Extending visual paths alone without the tactile instruction is not helpful. Multitask reinforcement learning improves generalization. The seen-unseen gap is narrowed. If we dive deeper, multitask learning benefits from more appearance of underrepresented words, as well as shared semantic encoding of the whole sentence. So the shared language encoder works better than the language encoders for individual tasks. To further improve the generalization power, we propose to learn a latent environment-agnostic representation that is invariant among environments. The objective is to filter out the environment-specific features that are irrelevant to navigation, preventing the model from overfitting to specific same environments. To do this, we add an environment classifier to predict the house identity, conditioned on the latent representation from the trajectory encoder. More importantly, we add a gradual reversal layer before the environment classifier to reverse the learning objective for trajectory encoder by reversing the gradients. Basically, the trajectory encoder is trying to increase the classifier's entropy and learns the environment-agnostic representations. If we remove the gradient reversal layer, then it basically becomes environment-aware learning. So we compare among RCM model, environment-aware RCM model, and environment-agnostic RCM model on two tasks. As you can see, environment-aware learning tends to overfit seen environment. It performs the best on seen environments, while environment-agnostic learning generalizes the best on unseen environments. And if we can combine environment-aware and environment-agnostic learning somehow to do meta-learning, then it may benefit from both worlds. We also plot the TSNE visualization of the learned representations. As you can see, environment-aware representations can be easily separated, and environment-agnostic representations are mingled together, which shows their effectiveness in representation learning. Okay, so now we have the final learning framework, environment-agnostic multitask learning. During training, the environment classifier is minimizing the environment classification loss, while the trajectory encoder is maximizing the classification loss and minimizing the navigation loss. The other modules are optimized with the navigation loss simultaneously. Okay, so paired with the single task RCM model, the single task RCM model with the environment-agnostic learning, and the multitask RCM model, you can see our final model achieved the best performance on unseen environments, and it significantly reduced the gap between seen and unseen environments. By the way, our model is ranking first on the CVD leaderboard. For future work, we consider adapt the model to outdoor navigation and learn a generalizable agent for all kinds of street view datasets. Thank you very much.